In this video, we're going to look at an introduction to determinants, and primarily we're going to focus on the learning objective of computing determinants of matrices using cofactor expansion. So the determinant of an n by n matrix, you can only find determinants for square matrices, and if you'll recall, we talked about the 2 by 2 case for a determinant, and we said that when the determinant is 0, then the matrix is not invertible, and we're going to generalize that now to n by n matrices. So we need a couple of notational pieces here. So we're going to use bars to mean the determinant of the determinant is just a scalar value. The determinant of a matrix with just one entry is the entry. The determinant of a 2 by 2, right, is A11 times A22 minus A21 A12. And for the largers, then we're going to need to define the minors and the cofactors, because we're going to do cofactor expansion. So if A is an n by n matrix, right, then Mij is a n minus 1 by n minus 1 matrix that we obtain by deleting the ith row and the jth column of M. And we call that the minor. So for example, the minor of A21. So I'm going to find the minor of A21, and I'm going to eliminate the column and the row containing A21. And you'll see there's my minor, and it's the 2 by 2 matrix that's left after I take out a row and a column. All right, so the cofactor of Aij is the determinant of the minor that we just talked about, and then we multiply by minus 1 to the, and it's the position, I plus j, right? So in this case of A21, I is 1 because we're in row 2, and j is 1 because we're in column 1, so 2 plus 1 is 3, so that'll be minus 1 cubed, which is minus 1, and then we just multiply the determinant of the minor. Okay, so now we're going to define, in general, the determinant of matrix A, and it is this cofactor expansion here. So it's A11 times the cofactor for A11 plus A12 times cofactor A12 along, and I can expand along any row or any column, okay? So I'm going to show you an example, a couple examples. So real quickly, just we've seen this, right? The determinant of a 2 by 2 is going to be what? 2 times 4 minus 3 times 1, and that's 8 minus 3 is 5. So now we're going to do a cofactor expansion along the first row. So let me slide this up for a minute. So I'm going to work across. So that's going to be 3 times minus 1 to the 1 plus 1 times the determinant of the minor. So we'll do it this way. And the minor is going to be, right, I'm eliminating the first row and the first column, minus 2 and 3, and 3 and 2. Plus 2, second entry, so in the first row, times minus 1 to the 2 plus 1 plus 2 times the determinant of the minor there. So eliminate the first row and second column, and you're left with 1, 2, 3, 2, right, plus 4 times minus 1 to the 1 plus 3 times the determinant of, and I'm going to eliminate that with first row and the last column, 1, 2, minus 2, 3. All right, so that's it. Now it's just down to the math, okay? So 1 plus 1 is 2, so that's going to be 3 times determinant of this is minus 2 times 2 minus 3 times 3 plus 2 times minus 1 times 1 times 2 minus 3 times 2 plus minus 1 to the fourth is 1, so that's plus 4 times 1 times 3 plus minus 2 times 2. Move down a little more here. So that's going to be 3 times minus 4 minus 9. I'm going to make this into a minus 2 times 2 minus 6 plus 4 times 3. It's supposed to be a minus, minus, so plus 4. And that's going to be 3 times minus 13 minus 2 times minus 4 plus 4 times 7. What is that? That's going to be 3 and 3 is 9. 3 and 3, let's see, so that's going to be minus 39 plus 8 plus 28. It's going to be minus 39 plus 36, which is minus 3. All right. Now, you can do that same operation along any row or any column. And I would encourage you to verify this by doing a cofactor expansion, say, along the first column. So that would be 3 times the minor, right? That piece will be the same. And then plus 1. And then you'd have these 4 would make up your minor, and so on and so forth. And you should get the same values. It's a good way to check you understand how to do cofactor expansion. All right. I did stick it into Octave just so we can see how to perform those computations. And so in Octave, the command is determinant, or DET. So there's the matrix. I just entered the matrix we just did and got the minus 3 there to verify my answer. All right. Let's take a second and look what happens if I do this. So now, this is a diagonal matrix, so what I'm going to do is be strategic and expand along the first column, right? So this is going to be equal to 2 times minus 1 to the 1 plus 1 times the determinant of minus 3, 0, 5, 4, plus 0. I'm not even going to fill those in because I'm expanding along that first column. Then 0 times anything is 0, so I don't have to do any more computations. So this is 2 times the determinant of this, which is minus 3 times 4 minus 0, which ends up being 2 times minus 3 times 4, which is minus 12 times 2, which is minus 24. You notice, if that's an upper triangular, that's always going to be the case. So we have a theorem that says that if A is a triangular matrix, then the determinant of A is just the product of the entries on the main diagonal. So I could have found the determinant of that matrix by just doing 2 times minus 3 times 4, because I know that it's an upper triangular matrix.